Good morning, everyone. Myself, Darshan BD, Assistant Professor, Department of EC, SJBIT. So today we are going to discuss the subject Introduction to Electronics and Communication, the Module 2 content. In that, we are going to discuss some topics on operational amplifier. Consider operational amplifier, the configurations. The three basic configurations for operational voltage amplifier together with the expressions for their voltage gain. So consider the supply line has been omitted from these diagrams for clarity, but are assumed to be symmetric about 0 volt. All the amplifier circuit listed have used direct coupling and have frequency response characteristics that extend to DC. So this, of course, it is undesirable for many applications, particularly when unwanted AC signals may be superimposed on an unwanted DC voltage level, or when the bandwidth of the amplifier greatly exceeds that of the signal that is required to amplify. So considering inverting amplifier with the feedback, the circuit of an inverting amplifier with a negative feedback and applied, for the sake of our explanation, we will assume that the operational amplifier is ideal. Now consider what happens when small positive input voltage is applied, that is, voltage V in is produces a current I in flowing in the input resistance R1. The operational amplifier is an ideal. We will assume that the input resistance, that is resistance that appear between the inverting and non-inverting input terminal RIC, so is infinite. The open loop voltage gain, that is the ratio of output to input with no feedback applied, is infinity. So with respect to inverting operational amplifier, so considering the diagram, so here we are going to apply input to inverting terminal. So we are considering the input applied to non-inverting means non-inverting operational amplifier. The inverting operational amplifier circuit, the signal is applied at the inverting input and non-inverting input is connected to ground. So this type of amplifier, the output is 180° out of phase to the input. That is, when positive signal is applied to the circuit, the output of the circuit will be negative. Assuming the OPAMP is ideal, then the concept of virtual short can be applied at the input terminals of the operational amplifier, so that voltage at the inverting terminal is equal to the voltage at non-inverting terminal. You can consider the voltage gain AV is, so V out by V in is equal to minus R2 divided by R1. So considering non-inverting operational amplifier, when the signal is applied to non-inverting input, the results shown in the figure, so it's called non-inverting amplifier. This amplifier, the output is exactly in phase with the input, means the frequency means phase is not changed. When the positive voltage is applied to the circuit, the output is also a positive. The operational amplifier is ideal. Then the concept of virtual short can be applied, that is, voltage at the inverting and non-inverting terminal is equal to, so AV is voltage gain, is equal to V out by VI. So V out by VI we can represent, so 1 plus R2 divided by R1. The gain of non-inverting amplifier is AV is 1 plus R2 divided by R1. Considering some differences, so differences between inverting and non-inverting amplifier. So consider the inverting amplifier, the type of feedback used in this amplifier is voltage shunt and negative feedback in inverting amplifier. In non-inverting amplifier, the type of feedback used in this amplifier is voltage series or negative feedback. The input and output voltage of this amplifier are in phase. Here in non-inverting amplifier, the input and output voltages of this amplifier are out of phase. The output of this amplifier is inverted. The output of this amplifier is in phase by the input signal. In this amplifier, the reference voltage can be given to the inverting terminal. In this amplifier, the reference voltage can be given to the non-inverting terminal. The gain of this amplifier is AV is minus RF by RI. The gain of non-inverting amplifier is AV is 1 plus RF by RI. The input resistance decreases because of the negative feedback in inverting amplifier. So due to the negative feedback, input resistance decreases. In non-inverting amplifier, input resistance decreases because of the negative feedback only. The voltage gain of this amplifier can be altered when less than or greater than or equal to 1. Here, when voltage gain of this amplifier is always greater than 1. So these are some differences in inverting amplifier and so non-inverting the amplifier compared to the gain, compared to output voltage, compared to the phase. So consider these are some the circuits related to inverting amplifier, non-inverting amplifier, and the differential the amplifier. So consider, so this first one is inverting amplifier. So in this inverting amplifier, we are going to apply input is applied to inverting amplifier with respect to the ground. The non-inverting terminal is connected to ground. So input is applied through Rin resistor to inverting terminal. Output voltage is, so we are considering this V1 and V2. So V2 is, since V2 is connected to ground, you can consider that V out is V2 minus V1. Since V2 is connected to ground, V2 is 0, so we are going to get output voltage is negative. So that's why, so in the non-inverting amplifier, output voltage is out of phase. Consider non-inverting amplifier, and you are going to apply so input to non-inverting terminal. So plus indicates that non-inverting terminal. So inverting terminal, you are going to make it ground through resistor. So V2 minus V1, so V2 is greater, the V1 is 0, so that output voltage is positive. So therefore we can consider that the output voltage in this non-inverting amplifier is in phase with the input. So third one is the differential amplifier. We are going to apply input to both the input, that is inverting as well as non-inverting. Output voltage is exactly that, the difference between the two inputs, that because the equation output is V2 minus V1. Since V2 is greater than V1, they are going to get the positive voltage. V2 is less than V1, we are going to get negative voltage. So from this differential amplifier. So we are going to consider some examples or applications of the operation amplifier. So consider the first one is the summing amplifier. A summing amplifier using an operational amplifier, so consider in the figure, we are going to apply different voltages are applied through to the inverting terminal. Okay, you can consider that V1 and V2 voltage. So V1 is, we are going to consider as a sine wave, V2 is a square wave. So you are going to get the output voltage like this. So it's combining the square wave and sine wave. The circuit produces an output that is the sum of the two input voltages. Since the operational amplifier is connected in inverting mode. The output voltage is given by Vout is equal to minus V1 minus of V1 plus V2, because we are going to apply input to inverting terminal. So Vout is negative symbol of V1 plus V2. V1 plus V2 are the two input signals. V1 and V2 are the input voltages. The input and output waveforms for a summing amplifier, we can consider this in the waveform, input and waveform for a summing amplifier. So you can consider this the waveform. The typical application of this is summing amplifier is for mixing the two input signals to produce the output voltage, that is the sum of the two input signals. Next we move on to integrator part. Integrator using as operational amplifier shown in the figure. You can see that, so in this figure we are going to apply input to inverting terminal through resistor R. Then we are going to use the capacitor so to give the feedback. This circuit provides the opposite the function now to that of the differentiator, in that its output is equivalent to the area under the graph of the input function rather than its rate of change. So consider the integrator produces the output voltage Vout is proportional to the integral of the input voltage Vin. An OPAMP integrator is an inverting amplifier which uses to a resistor in series with the input voltage and the capacitor C connected between the output and inverting terminal, means C is acts as the feedback. Actually the integrator converts square wave to the triangle wave. If the input voltage remains constant and it's other than 0, the output will ramp up or down according to the polarity of the input. The longer the input voltage remains at the particular value, the larger the value of output voltage of either polarity will be produced. Typical input output waveform we can observe here. This is the input and this is the output waveform. How the square wave is converted into the wave that has a triangular shape. Once again, note that output waveform is inverted because we are going to apply input to inverting terminal. We can come to know that the equation of Vout is minus 1 by R and C. R is the input resistor, C is the feedback resistor. The integral of Vin into dt. This is the equation of a integrator circuit. Then we move on to differentiator circuit. The differentiator produces the output voltage is proportional to the rate of change of input voltage. The differentiator produces the output voltage that is equivalent to rate of change of its input. If the input voltage remains constant, the output also remains constant. The faster the input voltage changes, the greater will be output B. So in mathematics, it is equivalent to differential functions. Okay, so you can consider that. So the equation also. So from this equation, so Vout is minus RC d by dt of Vin. Okay, you can observe here the waveform. So and the circuit diagram. Here we are going to apply input through capacitor and R we are going to use for the feedback part. So here notice that the square wave is converted to spikes. That the square wave input is converted to train of short duration pulses at the output. So you can see, observe that for the negative pulse we are going to get the positive spike because we are going to apply input to inverting terminal. So this is the differentiator, the part we are going to consider a differential input. Next one is the voltage follower. Voltage follower circuit, you can observe that Vn is you are going to apply to the non-inverting terminal. So output is same as input. Here the same output you are going to get. This circuit is essentially an inverting amplifier in which 100% of the output is fed back to input. 100% of the output is fed back to input. The result is an operational amplifier, so that has the voltage gain is 1, a very high input resistance and very high output resistance. So this stage of often referred as a buffer, because whatever the output we are going to get, that is same as the input, and used for matching a high impedance circuit so to the low impedance circuits. So considering a typical input and output waveforms, so you can observe, so in this the waveform. Okay, so you can consider that same the input and the same output we are going to get. Okay, this is called the voltage follower. So whatever output we are going to get, okay, so that is same as the input voltage. Next, the application is the comparator. So what is comparator? Comparator nothing but it compares the the inputs. Okay, so you can consider that the operational amplifier we are having the two inputs. One is inverting input, another one is non-inverting input. So we can use these two inputs for the comparison purpose. Since no negative feedback has been applied, this circuit uses a maximum gain of operational amplifier. Here we are not giving any feedback path. Okay, so we are considering in the network or circuit, we are not apply any feedback. We are considering the only the inputs, that inputs, different inputs we are going to apply to the inverting as well as non-inverting. Since no negative feedback has been applied, this circuit uses the maximum gain of an operational amplifier. It's going to get maximum gain. The output voltage produced by the operational amplifier will rise the maximum possible value, because we can consider that V out is V2 minus V1. So different voltage, so it's going to check that. Whenever the voltage present at the non-inverting terminal or non-inverting input exceeds the present at the inverting input, okay, we can consider V2 is greater than V1, so that we are going to get positive output. The output voltage produced by the operational amplifier will fall to the minimum possible value equal to negative supply whenever the voltage present at the inverting input exceeds the present at the non-inverting input. So we can consider that. So V out is V2 minus V1. V2 is greater than V1. We are going to get positive voltage. V2 is less than V1. We are going to get the negative voltage. So you can observe that input and output waveform for a comparator. You can see that this is one input, this is another input. When you are going to compare with that voltage, since we are going to use V1 is the constant voltage, we are going to use DC. So V2 is AC. So AC according to the variation. So this we are going to compare with the voltages. how the output is either plus 15 or minus 15 volt depending on relatively polarity of the two inputs. The application of comparator is that of comparing a signal voltage with a reference voltage. The output will be go high or low in order to signal and result of the comparison. Okay, so these are some applications of operational amplifier where we are going to use the operational amplifiers. Thank you.